there are not too many wells that are flowing now. 50 years ago, 70 years ago, many wells were flowing. It's not enough economically, the oil is not that expensive. Of course, there is a big pressure from the investors. Everybody forced to install some sort of pump. So right now, 90% of all the oil wells and even the gas wells, they utilize some form of artificial lift.
So again, thanks everyone for coming. Today's event is presented by Mr. Anton. Thank you very much for coming. Thank you very much for your time. Today the subject is artificial lift methods and the recent advancements in technology. I will read a little bit here from the small introduction that we have. This lecture will provide a comprehensive overview of artificial lift systems which are critical to the global energy sector for maintaining and optimizing hydrocarbon production. Mr. Shakirov here will explore major lifting methods, address current operational challenges, and introduce the latest technological solutions available in the market. So, Anton, I'm leaving this.
Thank you, Kostas.
Yeah, it was a quick one, but
that's enough.
Yeah.
Thank you all for coming. So very happy you guys attend. I'm not going to be too technical. I can talk for hours about artificial lift, but the purpose of today's lecture is just to give you an overview, to understand how oil is produced globally, what are the challenges, and how we select the artificial lift method. So looking at 120 years of from the first well in the US, at about the same time the wells were drilled, or even before that, they were drilled in Europe. We know Hungary and Romania, western part of Ukraine, that's where most of the wells in the beginning of 1800 were drilled. And at that time, you can see the investment to build a well was only $200 at the time. So in 120 years, oil and gas and the production increased dramatically. So, and you can see from 2014, Sakhalin Energy Arctic platform was built for $12 billion. Yeah, and I'll explain why it's still, a good investment. So this particular Berkut Arctic platform is one of the biggest in the world. I think it is the biggest, if it is the largest, if you even Google it. So it first of all, it's located in very remote area where you need to bring all the materials, you need to bring the people, so logistical, weather challenges. It has the drilling rigs, so it can drill the well. It can process the petroleum product in the same place. It has living accommodation for 200 workers. It generates power on its own, so it's fully autonomous platform, and it has a capacity of 90,000 barrels of oil per day, so it's basically $4.5 million of revenue inflow. So when you look at 12 billion and you understand that 4.5 is how much they can make, this is basically return of investment is only within 7-8 years. Yeah, you return the investment, and basically this platform can serve you for 70 years or so. So it's very reasonable investment size. At 2 million kilograms. Interesting thing that it can withstand the floating ice up to 2 meters thick. It can withstand the 9 magnitude earthquake and the waves of 18 meters tall. Yeah, so quite amazing where we got with the oil production. In 2022, ADNOC built the longest so far well, which has a measured depth of 15,500 meters long. So we can imagine that we're still operating somewhere in the crust. So actually we are not going too deep with the wells yet. Yeah, but they're becoming deeper and deeper. We can see that every few years there was some wells drilled in Angola. There were some wells drilled in Russia of over 10 kilometers in the length. But still, we're quite, narrow of where we're getting the energy from. Yeah. So, and of course, the energy consumption is growing. The top 3 charts that you can see, this is the oil, coal, and gas, and basically, oil and gas is covering for 53% of the total demand. And you can see all the renewables, which we're talking, still they're very, very low. Yeah. So only these 3 fossil fuels, they're still big on the market, and they basically drive our Earth's demands in the energy. Yeah? And when we look how much we need to spend to produce all this oil and gas, basically 57% or nearly 57% is used for pumps, so which is artificial lift. So we need to lift the wells. 26.6% used to maintain the pressure, because we take the hydrocarbons out. We need to maintain the pressure, so we're capable of producing for a long time. And the rest, 17%, is basically for other expenses. So well pumps is basically where we spend most of the money globally to produce the oil. So before we had oil, of course, the artificial lift was there, and basically for water, taking water from the river, taking water to the house. And there were many methods which you can see it even until now. They look in the same way, like the one on A, you can see top left corner. It looks like a sake rod, yes, so the one we know. So you just lift everything, you take mostly water for agriculture, the water for houses, etc. Still we're doing something similar, but there was no oil, basically. Later on, you can see, and it all started in the ancient Persia, in Chinese dynasties, and in ancient Egypt as well. So there are many applications where people used water. And as we can see, first it started with a person which is lifting something, but then a sort of machinery was used in a form of like animals. So we used camels, and we used cows in this case, and horses, of course. So if we look at what Richard Spears is one of the top famous guys in artificial lift, especially in the business. So how he's describes what is artificial lift in general. So this is a type of equipment which is installed within the well to support the pressure in the well. Yes, so to lift the fluids from the bottom hole to the surface. So right now, 90% of all the oil wells, and even the gas wells, they utilize some form of artificial lift. So there are not too many wells that are flowing now. So if we would look at 50 years ago, 70 years ago, many wells were flowing, especially in the GCC, in the Gulf countries. But now they install the pump, or some form of the pump, because it's not enough economically. The oil is not that expensive. And of course, you want to produce more. Even the well would be flowing to, say, 100, 200 barrels. They will install a 5,000 barrel pump, just to extract as much as possible. Too, of course, there is a big pressure from the investors to return basically their expenses on the drilling, etc. So everybody forced to install some sort of pump. And main forms, we'll discuss 3 of them, which is the rod lift. So basically, we use rods to lift the fluid from bottom hole to the surface. Gas lift systems, where we inject gas in the well, and electric submersible pumps that are so-called ESPs. So they're producing most of the oil, and they're used now for geothermal. They're used now to lift water wells. The same technology is used to transfer the production liquids from A to B and inject it downhole. So we call it an ESP. Yeah. There are different forms. So totally now on the market, there is, 25, 30 methods how to lift the well. But like 60% or 70% of them will be these 3. So the rod method, the gas lift, and ESP. So how do we choose what kind of artificial lift to be used in a particular well? Of course, we need to understand how much to produce. Yeah. So there are some methods that are good for low production. Some methods are good for high production. We need to understand how deep. And of course, the deeper we go, the temperature increases. So we need to look at the material selection, the insulation properties. Very important is how much solids to be produced, how much free gas will be there. So will pump continue operating, or there will be gas logs, etc. All the problems once we go for oil well, there are all sorts of problems. There is emulsions formed in the well. We can have scales, different types of scales. We can have sand production. So all of these parameters, also the deviation, can this pump go through a deviated section? Because now most of the wells are drilled, they're slant, like they have an inclination. So you need to make sure you're going to pass the deviated sections and safely set the equipment somewhere inside the well. And Now artificial lift is used for the wells up to like 5,000 meters, so it's quite deep. So when you look at the applications, I mean, we see a lot of high gas applications, high temperature, etc. Of course, the price is the most important. So when we choose an artificial lift method, like Sakhalin pumps or versus jet pump or ESP, we need to look at how much is going to be producing, for how long. And basically, these are all the factors that are affecting the selection. And it's quite detailed process, because you may want to start with one type of artificial lift, but later on, for example, you get more water cut, so more water production over the years, because you do pressure maintenance with the water. So at some point in 10 years, 15 years, you will see more heavier fluid, and maybe this, like the gas lift, which is affected significantly by the content of water, it may not be good enough for in 10 years. So a proper strategy should be built for a field or for a group of fields, where we say we're going to start with this one, it will achieve these parameters. Later on, we're going to shift from one method to another, or maybe we shift for a group of wells. We can keep the downhole pumps for one type and gas lift for others. But I'm not going to talk much about this. So let's look at the most common, the most, I would say, easiest way to produce the well. So like we did it in the pre-oil era, where we only produced water. So we're using the rods. So basically we have a pump jack on the surface, which is connecting a downhole pump. Let me show you. So the downhole pump is here, and it's connected, the surface and downhole connected with the rod. What is the rod? It's just a piece of, basically a piece of steel. So like a rod, yeah. We connect them every 9 meters or something. We length to the depth we want, where, for example, we have a perforation, or when we have inlet of the fluid, and basically going up and down with different speed, with different stroke length. We can go very long and slow, or we can go faster but shorter. And what it does, it's very simple. There is only a barrel downhole, which is filled with oil and pushed. With every stroke, we push this amount of production of this volume of the liquids, we push it up. So for example, if our stroke length is like 3 meters, so every stroke we push 3 meters up a certain volume. And of course, clearly this type of pumps are for low production, so you cannot lift too much, because you have this stroke of 3 meters, you have limitation inside the tubing, so you can fill up some area and you push it up. But of course, there is some companies that are doing different type of sucker rods now. They look totally different, and we call them long stroke systems, and of course they can produce much more. So I would say in this conventional design, the maximum production should be like say 1,000 barrels a day, 1,500 barrels a day maximum. So if you go over 2,000 barrels a day, you need a longer stroke system, and there are better methods for that, in fact. Yeah, so this is the oldest. It's cost effective, because all you need to replace when the pump fails, the downhole pump, so you need to change this pump. And it's when we look at 800,000 wells globally, they are sold for 3.1 billion a year. So every year there's contracts released for 3.1 billion a year. And if we just recalculate how much you need per well, it's like $4,000 per well, because you really replace only this small pump, which is downhole. The surface equipment is your capex, and you build it once. You can use it for 50 years, for 100 years with a small maintenance. And so it's very cost effective, but again, for low and medium rate application. So before like 1900, that was the only method to be used in the world. Recent years development show, of course, improved rod materials. So you can make more robust rods, so they're harder, they're corrosion resistant. Also, in some companies apply continuous rods, so that don't have connection in between. So it's like a single piece, which is going through deviated well and operates the downhole pump. Of course, improvement on the motors technology. There is a lot of automation, like including AI. And those two main problems that are in oil and gas, the gas handling, because it's a pump, so it cannot pump gas, so it can pump liquid. So some different technologies were introduced to handle solids and gas, so to extend the run life, basically, of downhole pump. Because once the pump is failed, you need to pull out the rods, you don't produce these days. So it's very important that the run lives are very, very long and you have minimum non-productive time from the well. This goes number two, based on number of wells, it is smaller, but based on the revenues, it's way bigger because ESPs are used for all kinds of applications globally. Basically, it was designed by this guy poor guy from Armenia who struggled a lot for about 30 years or 20 years. He was running around different countries and tried to gather some investment, attract some investment to company. He was from Armenia, so he went to Moscow, was rejected. They said, why we need this pump? Its flow rate is too high. I mean, nobody's producing the wells with the high flow rates. So we just keep the socket rods, like the pump jacks, yeah? So then he went to Germany. He was declined again. Then he went to Oklahoma in the US, and he met a gentleman who was one of the founders of nowadays ConocoPhillips, Mr. Phillips, before they joined the company. Yeah? So Phillips believed in this idea because he understood that the flow rates will be increased, the drilling is being increased, I mean the capacity of drilling rigs. So he invested, and right now this is the major lift method which is used globally in terms of the capacity, how much oil is produced. So some people say 85% of oil produced with this system. I think it's a close number. So we see the huge market. We see different applications because this from 1934. So he designed the system. So it's a tubing deployed system consisting of a multi-stage centrifugal pump. So stage. We have some protection devices like the gas handlers. And we have electric motor, which is powered by an electrical cable coming from the surface to the downhole motor. So what he did, in fact, Mr. Arutyunov, he increased the speed. So he designed a higher speed device. So by having a higher speed, the head per stage became higher. So he could reduce the diameter. So this surface pump, which was used everywhere in the industry, became smaller. So it became slimmer. Number two, he said we can build the pumps as a multi-stage. So not only one stage which is delivering, for example, 5 meters of head. I need 2,500 meters. I want to lift from the very deep conditions. So he designed the concept of multi-staging, and by adding stages, he could lift the fluids to from a higher or deeper wells. Of course, the electric motor was there, Tesla was there, electric motor asynchronous was on the market, but it was too big. So he also designed it for a higher speed, slimmer, so he can put everything in the well. And basically, that was the first high volume system. Over, I think, 40 years from this invention, his company, Rida, which is a Russian electrodynamo Arutyunov, which is now part of Schlumberger, it was in the 90s, it was acquired by Schlumberger. They were a complete market leader for high flow rate applications. So they made so much money, they sold the company to Schlumberger. Now I think Schlumberger, they're making probably close to $2 billion in artificial lift. So every year, so everywhere, in offshore, in onshore, deep wells, and it's still growing. I'll talk about the market a little later. Now the modern systems, they look differently. They come. Sorry, I'm using my marketing slides because I don't have other ones. So you will see logo from time to time. Basically, system consists, the ESPs consist of two portions, or I would say three. So you have the surface equipment. The box on the left, we call a VSD, variable speed drive. It's basically the brain for the motor. So you can set up what kind of speed you want to operate, how you protect the equipment. If there is, for example, not enough inflow from the well, you want to make sure you are protecting the equipment, you are controlling the equipment. And you do it with a 380, 480 volts, like a normal industrial power supply, 50 or 60 hertz. But the downhole motor requires higher voltage. It's a high voltage device. So we need to have a step-up transformer, which is bringing the voltage up to support the cable losses going downhole, and of course the high voltage operation of the motor. So in this system, you can see it's a rigless system, which is deployed on a cable. So you can see from the surface with the wellhead, the red wellhead, we deploy the system completely on the cable, and this cable is holding the ESP, downhole ESP, in place, and it's also providing the power at the same time. Yeah, in this configuration, of course, the motor will be on top. There are some gauges and protection devices, and the pump will be on the bottom. But if we deploy in a conventional way, then the pump will be on the top, the motor will be on the bottom. But it's a matter of configuration. So with this type of pumps, we're capable of producing up to 3,000 HP wells. So you can have two pumps in a well connected with white tool. You can have basically all kinds of like super deep wells. You have the wells for SAGD, if you know SAGD, like where we produce the heavy oils. So many applications. And this market is the biggest out of artificial lift. It's 7.3 billions. And only 200 wells or so. Some say 300,000 wells, but I think 200,000 wells in general is a good number. So if you divide how much per well is spent on this type of pumps, it's 35,000 per well. But the price can go up to 2 million per well. Because if you talk about like offshore Norway, very tight, very strict safety, QHSE, very expensive to make the workover, basically high horsepower, etc. So per well, a client can spend up to 2 million. So recent developments are around like increasing further the speed. Like Arutyunov, he increased the speed to 3,500 RPM. Now most of the companies are going to 10,000 RPM or even more. So pumps become slimmer. They can be deployed on like the cable. They can be deployed on a coil tubing. They can be deployed on a slick line. So because the rigs is a big issue in the world. Yeah. So if you have a pump failure in Malaysia offshore, first of all, you're going to be waiting for 3 months for rig to come to replace your pump, to pull all the tubings and install a new pump. So first of all, you lose production for 3 months. Secondly, you're going to be paying $400,000 per day to do the rig. So many companies prefer, especially offshore, to run pumps riglessly, run on a slick line, coil tubing, cable, or something else. In that case, you can keep the tubing in. Even the big pump has failed, you can install straight above the pump inside the tubing, so you start producing and wait for rig. Still, you need a rig at some point. Like in India, the rig wait time, India offshore, like ONGC, government company, it's like 6 to 8 months, 9 months sometimes. And again, the prices are very, very high for the rigs. So more compact systems, higher efficiency motors, and of course, fighting with gas and sand, like for every artificial lift, and a lot of automation nowadays that can further optimize the hardware we have in the well with the software. Some tools allow for more production, so the AI will find what is the best operating speed. So it will check the well and basically make sure the maximum is produced from the well. It will go away from some failure modes. So for example, it can see that there's more sand being produced, so it will slow down the pump, to basically save for the erosional effects. Last but not least, gas lift is something that was developed also to lift initially water wells. So they've injected air. This small area, so we have a tubing inside. You can see the tubing. And outside of the tubing, we call an annual space between the tubing and casing. So in an air lift, originally they've injected the air. So air would get through, you can see it goes down to the well. It enters the tubing. So by introducing air into the water, basically we reduce the density and we reduce the weight. So then it will lift the fluids up. So we add air energy to the well. But of course, once the oil era started, we cannot inject air because there is oxygen, and we talk about hydrocarbons and oxygen, basically a small spark and you have a failure. So it has been decided in 1900s to transition to injecting natural gas instead of air for safety measures. So this system also allows you to produce many types of applications. So you can use it in low rate wells, in a high rate well. So it's case by case. Very little maintenance because you only inject gas. So, I mean, there's no pump to fail. If for example, downhole valve fails, that is used to inject the gas introduce the gas into the well, it's very easy to pick up with the slick line to pull the valve, install a new one. So very low maintenance cost. And of course, there are no moving parts like in the Sakhalin pump or ESP, which basically is forcing the fluid. You rotate or you do the upstrokes and downstrokes. Here we can handle solids, we can handle gas. Gas is actually good. And there's about 100,000 wells globally, mostly offshore, I would say. A lot of wells in Asia, in Central Africa offshore, in the Gulf of Mexico, in many places. But typically here you would need to do a big capex upfront. So you need to build all the gas compression systems, which you're going to be using to drive many wells. So you don't do gas compression per well. You will do gas compression for a field of, say, 300 or 1,000 wells. Like in Algeria, there is 3,500 wells that are driven by gas lift. So, and in that case, you don't need electricity. Like for ESP, electric motor. For Sakhalin pump, electric motor. Here, you don't need to have electricity. So it's very good offshore to have a gas compression on one platform. And basically the rest of the wells you can drive with your pressurized gas. Yeah. So many advancements here as well. Once again, I'll point out that here per well will be only 12,000, and you don't really you don't use anything expensive in the well, so only the valves, which you can retrieve and you reinstall. So very cost-effective method, but the capex that you need to put upfront to build the network, to build the gas compression systems that are crazy expensive. Of course, you do it only once when you build the field. So sometimes they need to be upgraded, but I wouldn't say it's a big expense later on. So recent developments include electric gas lift system. So we can control from surface, open and close the valves to optimize the gas lift rates. Of course, many improvements with valves and mandrels, where the valves are installed. We call them mandrels. Higher pressure systems, like in, say, in West Texas, they don't care too much about the power consumption because it's more driven about getting the back investor money. So they just go ahead with the high compressors, individual compressors for the well, and they just pressurize to as much as they can to get maximum production from the well. So it's a great system as well for quick return of investment, because you drill the well. It's going to be like $2-3 million, depends on where you drill, but say US onshore, like West Texas will be, say, 2-3 million. I'm not sure exactly, but you want to get back this 2-3 million as soon as possible. You don't care about efficiency. You just need to get as much oil as you can within 6 months, and basically pay your investors back. So when we look at the oil and gas as a whole, so let's start from the right side. So oil and gas market is increasing significantly. So we can see growth of 70% over 4 years. Because 2020 was very low, because of COVID. We remember what happened to the oil price. So from 2020, it just picked up so quick. You can see from 6 trillion, it goes to 10 trillion. And oil field service market is following that. And it's basically a portion of what is oil field service. You need to drill, you need to maintain the well. Of course, pumps are part of it. And artificial lift market accordingly is growing because more and more wells, they require a pump. And ESP, it's about half of the whole artificial lift market. So because they produce most of the oil. Yeah, we can see that the market was growing till 2019. In fact, it was growing steadily. 2020, 21 were kind of flat, and we went down because oil was not used. I mean, it was not in demand because less traveling, less fuel consumption. And of course, the markets were steady. And since then, we can see the projection made by Spears and Associates is showing a steady increase to $17 billion. So that's the amount of cash spent every year to buy pumps. As you can see, every year more and more cash is spent to buy all kinds of pumps. So this will include the ESP, the Sakhalin, the gas lift, and other forms which are minor like the progressive cavity pumps and hydraulic systems. So how they make money here in this business? Always there is a lot of engineering involved, and if a company wants to produce their wells, first they do the engineering study. So they need to understand what kind of technology, how much they need to spend to produce. And as I mentioned, 90% of the wells, they require some sort of artificial lift, so selection is very important. So in general, there are two models. One is when an oil company, they would buy the pumps and they request the service from the manufacturer or from a third party. So there could be, for some companies, it's a great model because basically for a private company, they have it on balance. So their capitalization is growing. They spend something, they own it, the ownership transferred to them. And a smaller operators, typically, they are forced to pay up front. And those operators that are located in some unsafe areas, like as a pump manufacturer, you won't send your equipment, for example, to a country that has a risk of revolution or some coup, and a lot of countries that are producing oil and gas, unfortunately, they're affected by this thing. We know what happened in North Africa, in the Middle East, and in other areas. So now everybody talk about Venezuela as well. So we hope it's going to be sorted out soon. But as artificial lift providers, companies are very careful how they will be guaranteed to get paid. So they ask for upfront if it is not a 100% comfortable situation. For some cases, there could be like a partial payment. So in that case, an oil company co-finances a pump manufacturer, because we can talk about thousands of wells here. So imagine if one well is in average, say $250,000, and you get an order of like 1,000 wells. So it's quite big amount of cash. Like there were recent tenders in the Middle East where a tender award was like 1.5 billion among several, $1.5 billion US among several manufacturers. So, and of course, the top clients, they never pay you upfront. Like if we talk about the biggest names, typically they will pay you or pay the manufacturer when equipment is delivered or it is installed and running in the well. What we can see on the market now, a lot of oil companies, they're moving towards rental. So they don't want to pay upfront. They want to pay you kind of when they produce oil or when you provide the services. So in this model, a contractor or a manufacturer of form of artificial lift, they will be delivering everything at their cost. They will do installations. And when the client starts producing, they will invoice every month. So, for example, this month 30 days, so many pumps. Another month is different, and they also pay when oil is produced. So I've seen contracts where they stop paying you if they don't produce. For example, there was a case with the one company in the Middle East where they stopped paying the ESP vendor because it was part of the contract. They didn't want to produce when oil is $25 a barrel or $20 a barrel, and they stopped paying the vendor. So there are risks from basically not only the oil producers, but the vendors as well on the market. Looking at the technology pipeline, like what we touched a little bit, that the big issue with the gas, and going from the left to the right, you can see different solutions on the market. So very industry standard is the separators. So when we separate the gas to save the pump. In some case, an advanced handlers can be used. So those are kind of multi-phase devices that can put the gas into solution. So they pressurize the fluid, and because of higher pressure, the gas goes back into solution. There are some modern technologies like the helicoaxial pumps that can do up to 90% of free gas. And the next phase is basically when the companies will go towards even higher gas content. And we're talking about 97% of free gas. So very little oil is produced, but with a lot of gas. So why we get more and more gas every year? Because the pressures, naturally, they go down. So we produce from a certain depth. Initially, the pressure could be as high as 300 bars, 400 bars here. But as we produce the field, even we maintain the pressure, still it's going down, yeah, so naturally. So when the pressure goes down, downhole, more and more gas released from solution, from the oil, because they live together in the reservoir, yeah, so we always have gas on top, we have oil, and we have water, basically 3 layers based on the density, yeah. So that's a big challenge, and but the good thing, there are some technologies that are already getting there. So a lot of trials being done with the helicoaxial, with the Tesla pump, which is a boundary layer pump. So many activity, and I've spoke to the biggest clients, like globally. They all expect in like 10, 20 years to get more and more gas. So that's one of the key areas of the development. Second thing, wells, as we just discussed about the longest wells, they get deeper, they get slimmer. So manufacturers are forced to produce more from the same well, and going from say 1,000 barrels for a slim application, going to 2,000 barrels or 3,000 barrels a day. Again, because of the low oil prices, pressure for efficiency from the market, from the investors. So that's one of the areas to increase the production of a slim well, to basically do better ROI. Number 3 is same concept, like getting higher speed, getting more efficient. We can see on the surface applications. And here you can see a horizontal pumping system, which is an industry standard to transfer the fluids, to inject the fluids for pressure maintenance. Even surface equipment becomes smaller. So those many platforms that were built like 50 years ago, they don't have enough space to put a long 15-meter or 20-meter long pump, because it's only 20 meter. So there is a lot of pressure to save on the footprint, to basically do the more pressure maintenance, more injection packages. In many countries, it's in requirement, yeah. And of course, when we go to geothermal now, globally, we can see more and more geothermal, especially here in Europe, like on the mainland. Unfortunately, in Cyprus, we don't have. We have quite low temperatures, I think, ranging from like 60 to 70. So it's good for residential heating, but unfortunately, it's too low to generate electricity from heat, which is they do a lot in other countries in Europe. So when we talk about artificial lift for geothermal, of course, we're looking at very high temperatures equipment build, so it can withstand like 170 degrees C or even more. So I've seen some wells in Europe that are going to like almost 300 degrees C. So imagine all this equipment should be rated like a spaceship, yeah. So it should withstand high pressure, it should withstand gas, which is associated for both for oil application and geothermal, and everybody expect it to last like 2 or 5 years. So it's very high rated devices. That's why the reason they can cost up to $2 million per well, yeah. So looking at like what's on the market right now, of course, what we call a universal ESP is like an industry standard. So it sits straight in the middle, so it can cover water wells, it can cover like a standard ESP solution. Yeah, so it's most of the market, most of the money spent for the universal. We call it the universal ESP because they can be used in various applications. They can be used for water, for agricultural, they can be used for geothermal production, they can be used for oil and gas, and it's like an industry standard. When you go to the right side, so there are 2 technologies, which is the through tubing ESP. So that's the small ESP, slim ESP, that can go without using the rig. So it can be installed on some sort of deployment system. And it has one of the biggest potential on the market. And going high speed, which is ultra high speed ESPs, Lex be the pioneer in this domain, but other companies also try to pick up, because you basically get the most compact equipment. It can run longer, it saves power, it's much better for the environment. And some other technologies include like modification for the gas lift equipment, which is a turbox gas lift. jet ESP, where you can combine two methods in the same well. So something I did mention, we also have an opportunity to mix the methods. So we can have the Sakhalin, for example, the Sakhalin rod will be at the bottom of the string with the rods, and on the upper side of the string, you can have a gas lift mandrels. So you can mix the methods. And when I was talking about the selection of artificial lift methods, this is something we're always identifying, like what is the best pure method or a combination of the methods. You may have an ESP, a downhole electrical equipment, and a gas lift on top. So you inject the gas in the upper section, but you produce main production is from the ESP. That's all I had.
Very well. You gave a very good idea of what is artificial. The technical bits can come later on, and we will do monthly, as we discussed, seminars like that, so that people will understand more the technical bits of the things. But